time for plenary speaker for the meeting this time. Eric Corwin is a professor at the physics department at the University of Oregon. He works on complex behavior from simple interactions, such as extreme diffusion and ideal glasses and ideal disk packing. Eric's going to serve as my mentor along with Oksana for the Pivot Fellowship. He's between the three of us, we're trying to combine theory, large-scale computations, and experiments, and try to make a connection. He's the large-scale computations guy, or I'm told. And yeah, so please, Eric. So thank you.
Thank you very much. This is great getting to visit and meet you all. So during this talk, please interrupt with questions. It's more fun. Yeah, just shout it out.
Sorry, could we turn off one or two of the lights? It's a little washed out.
Yes. Most of it.
Better?
Yeah, that's great. Most of the talk is on like that. So what I'm going to talk about is, I think, very different from what all of you have shared today. I'm going to talk about something called the Gardner transition, which shows up in glasses and jammed systems. And this is work that was done with a couple of former grad students, so Cameron Dennis and Andy Hammond. So the big question when thinking about glasses is glasses themselves are simple. They're not quite trivial, but they are a material that people have been using forever. When I say glasses, I mean, glass, like window glass, glasses that you wear. We can make anything we want out of them. We know how to use them. We know how to treat them as a technology. They're a very, very well understood and well controlled technology. The thing that makes glass so special is that unlike most crystalline solids, it doesn't have an abrupt melting point. If I put a chunk of ice and a chunk of glass in your hand, and they're both at, negative 30 degrees, they feel like they're the same thing. They're both hard, they're both sharp. If you drop them, they both shatter. But as you warm them up, right at 0 Celsius, you get a puddle of water with the ice floating in it. So you get this coexistence. If you warm up the glass, it just continuously gets softer and softer and softer. And this is what makes glass so valuable. This is why all of the plastic cups that you're drinking out of were, cost essentially nothing, because they can be formed just by heating and then pressing. You couldn't do that with ice. You can't blow a chunk of ice into a goblet. So glass is a really wonderful material, and we can understand it sort of in large scale. It's this dynamical arrest of a liquid. It's in a steady state. It has an unchanged structure, which is to say that if you were to look microscopically at the structure of glass at room temperature or the structure of liquid glass at 600 degrees, it would look the same. A microscopic snapshot would look the same. They only differ in that the room temperature glass is arrested and not flowing. At high temperature, it's flowing. And this is all driven by thermal fluctuations and entropy, and it's all straightforward. The glass transition, on the other hand, is hard. The glass transition is how is it that you go from the glass that is molten, that you can blow and pour and treat like any other liquid, to the glass that is a solid. So we know that as you cool, something happens and it stops being a liquid and it becomes a solid. But we don't have a good order parameter because it's a disorder to disorder transition. So it's not like we can say, oh, it crystallized, just look at order parameters of structure. We don't even have good dynamical order parameters. It's hard to understand what's going on. We don't have natural small parameters to expand about and to understand our phase transition based on You know, that small parameter being the only thing that's important. So all of the things that we do with phase transitions, we can't do with the glass transition. And then to make things worse, there are multiple things going on. The most serious of which is that the glass transition involves ergodicity breaking. And the way that you can see this is if you take liquid water and you freeze it, on a small scale, you always get the same crystal. If you take liquid glass and you cool it, the structure is entirely determined by the structure that it had right before you cooled it. So you get stuck in a different part of the phase diagram each time, or not phase diagram, of phase space each time you do the experiment. So the glass transition is really, really hard. And then we introduce an analogy. The jamming transition is also hard. And if two things are hard, maybe they're hard in the same way. So the jamming transition is something that you may not be as familiar with as a term, but you're all very, very familiar. You go to the beach and you make a sandcastle. What you've done is you take your bucket, you scoop up sand. And so in scooping it up, maybe you pour it into a bucket, you pour it and it behaves like a liquid. And then you press it a little bit and you pop it down and now it's a solid. And so the jamming transition is the transition of athermal granular materials from a flowing state to a non-flowing or rigid state. And this jamming transition is just absolutely ubiquitous. Anytime you scoop rice, right? Why is it that you're able to run your scoop through that rice? And then you could take, I don't know why you would do it, but you could take your big bag of rice and you could stand on it and it would support your weight. In fact, you could stand on it while scooping it at the same time. So it is able to be both rigid and flowing. And what controls this is something about how each individual grain interacts with its neighbors. So I've shown a bit of a sort of simplified version of this. At low density, low packing fraction, we have everything unjammed, which means that if you were to grab hold of one grain, you could move it around without problem. At high density, everything is overjammed, and thus in between, there must be a critical density at which things become jammed. You can also think about this in terms of crowding or frustration. You imagine if you get on a bus, if the bus is crowded, in order for you to move, somebody needs to make room for you. But in order for them to move, somebody needs to make room for them, etc. So you get on the bus, the entire bus full of people needs to move in order to make room for you to get onto it. So that is the sort of overjammed state. However, if nobody's on the bus, you get on, you can go and sit anywhere you like. This is the unjammed state. And then the critical jammed state is right in between. So anything I forgot to say here, so that the model is just athermal repulsive particles. It's this transition from floppy to rigid. But again, it is a transition from disordered to disordered. And so the fact that it is disorder to disorder transition, where you go from a flowing state to a rigid state, suggests that this is the zero temperature version of this glass transition. We can make this even sharper by thinking about not a physical glass, but what we call a hard sphere glass. So imagine exactly this system, but now give it some thermal energy. So everything's jiggling around. Here, everything is jiggling around and everybody can explore everywhere. Nobody's getting in one another's way. Here, nobody can move. The state of the system is stuck. It is a glassy system. And then here we have this transition. So trying to understand this transition is our goal.
I have a question, and maybe you'll get to it. How does dimension play a role?
That's a really good question that we spent years answering. So the short answer is that a lot of the stuff I'm going to tell you, dimension plays a crucial role because we take the limit of dimension going to infinity. Dimension, in fact, inverse dimension takes the place of this small parameter. And as dimension gets higher and higher, the system becomes simpler and simpler because you can think of the system just in terms of the interactions of a particle with all of its neighbors. And you never have to consider the possibility of a particle's neighbor interacting with another neighbor of the particle. Because as you go to higher and higher dimensions, you share a vanishingly small set of neighbors in common with each neighbor. The thing that is the surprise is that all of the calculations that we make for infinite dimensions, we can then predict, that if nothing interesting happens, what would they do down at physical dimensions? They all work really, really well.
You analytically continue the dimension parameter?
So that's not the worst analytic continuation that we do.
Okay.
But yes, you do. And in fact, I'm not going to talk about it here, but you make very precise predictions about scaling exponents to several decimal points that obtain all the way down to d equals 2.
Mhm.
So dimension plays a really important role, and we simulate dimensions up to, depending on what we're doing, 8 or 13, or people have gone to 20. And we see the infinite dimensional behavior. And then we see the infinite dimensional behavior holds all the way down to d equals 2. Falls apart when you get close to 1, but that's, I think, expected. So our question is, are these really the same thing? And to answer this, I need to give you a short primer on Gardner physics. So Gardner physics is so Elizabeth Gardner was a physicist who sadly died very young, in her early 30s, in I think 1989, but she worked on spin glasses, and she pioneered this idea of a Gardner transition, and this is what I'm about to tell you. I go too far. So this Gardner physics is built around an idea which, are any of you familiar with this idea of a replica trick? Maybe not. Good. So the idea behind this is, let's say that we have a system subject to disorder, and it is a thermodynamic system. So we can write its partition function z. And moreover, we can average that partition function over the disorder in the system. And we would like to think, cool, that tells us everything that we want to know, because if I know the partition function, then I know the free energy by taking the log of the partition function. And from that free energy, I can get any thermodynamic or statistical mechanical property that I want. I have, in essence, totally solved the problem. The problem is that if I were to take the average partition function, averaged over that disorder, the log of the average partition function is nothing. It's not a thing that tells us anything. It is not the average free energy for the system. The average free energy of the system is the average of the log of the partition function. So it's this subtle, annoying thing where the order in which we take the average matters. So what we do instead, so, write it here, if we have the log of z, we can write the log of z in a way that doesn't feel helpful. So the logarithm we can define as the limit as n goes to 0 of z to the n minus 1 divided by n. You may have seen this written out this way in the past. You may not have. It doesn't really matter. The one thing that's a little bit interesting about it is it gives a little bit of teeth to the kind of obnoxious thing people sometimes say, which is that the logarithm should be thought of as sort of like a power law. That, the power law below 1 isn't a constant, but actually a logarithm. Maybe you've never heard that, in which case it doesn't matter that it's giving it teeth. But this is the idea that the logarithm is the limit of this power law, minus 1 divided by n as we take n to 0. So then the game is if we want to know the behavior of, there it is, the average log of z, which is the average free energy associated with our disordered system, where the average is an average over the disorder. What we can do is propagate this average inside and say that it's the limit as n goes to 0 of the average partition function raised, or the average of the nth moment of the partition function. So z to the n minus 1 divided by n. So far, this doesn't seem very interesting or relevant. Where it becomes interesting is the realization that for a partition function, z to the n is nothing more or less than the partition function of n copies of our system. So if we were to take n copies, independent copies of our glass, and let it evolve in time, this is how we would measure the average partition function z to the n. Then we need to do an analytic continuation, and this is the one that is, I think, much sleazier, where if we're thinking of the partition function as n copies of the system and averaged, we can calculate z to the n for integer values of n relatively straightforwardly. And then we need to take the limit as this n goes to 0. And to do that, it's unbounded. It's an analytic continuation. And this is the reason why this replica trick is something that's not on firm mathematical foundation. Despite that, it seems to work really well. And so this is the game that people play. So the idea is, again, that we learn about systems with disorder by imagining a large number of systems that are identical and allowing them to evolve independently and then letting n goes to 0. When we do this, we make these calculations and everything goes great. And then what shows up is that there are places where these calculations go awry. Those places we're going to talk in terms of replica symmetry breaking. So the big question is, if I have multiple copies of the same system, do they always behave in the same way? So we imagine liquid, which is something that we would call replica symmetric. And I know that this is not a particularly meaningful way of representing this stuff, but there, I don't think, is a particularly meaningful way. So the idea is we have some energy or free energy surface in our configuration space, and we're at some temperature, and so we're able to explore within it. If I make two copies of the system, in this case, the heart and the star, I plunk these identical copies of the system down, and then I allow them to evolve thermally and independently. So I could prepare them, absolutely identically, but then I let go and they take their random walk through configuration space because they're subject to thermal forcing. They will, at very long times, explore this entire space. And then within this replica symmetry sort of formalism, the question that we ask is, how similar are these two copies? And what we're going to find is that it breaks down into two pieces. If I ask how similar is the state of the heart system to itself, well, it's always exactly similar. Then if we want to, you can give this notion of similarity a little bit of teeth. You could call it the overlap between the replicas. Sort of drawn here are systems of hard spheres. I think these are hard spheres, where I've created two identical systems and allowed them to evolve. And so the overlap is literally the overlap. Take the copies of the system, put one on top of the other. Here in gray is where the systems are the same. And then wherever it's colored, this is where they differ. So you can see, in the two systems, this particle here has either, a choice, did it move up or did it move down? And so we can ask for the liquid at long times, every pair of systems are going to be equally distant from one another because they will explore this whole system. And so their overlap, we would call it some value Q0. And Q0 must be bounded between 1 and 0. 1 meaning perfect overlap, you can't do better than perfect overlap. 0 being absolutely no overlap, you can't do worse than there being no overlap. So this is what happens if we have a liquid. So if we imagine we're cooling our glass, our liquid into a glass, and as we cool, it stays a liquid, which means that it's ergodic. We can explore everywhere. So we will. So our overlap is just this diagonal with the off diagonal term is Q0. This is a state that we would call replica symmetric because every replica is essentially symmetric. We can form a stable glass if we undergo a single step of replica symmetry breaking. What this means is if our energy landscape fractures into independent basins. So as we're cooling, you get stuck. Wherever you were, you get stuck. And if you started somewhere else, you got stuck. And so what we have now, we have our energy landscape, and it's got a big barrier in it. And so there are two parts, and you should really think of this in a very high dimensional space. And it wouldn't be two, but it would be an extraordinarily large number of independent basins. And now we have a hierarchy. So again, always the diagonal of our overlap matrix is ones, because you are always exactly identical to yourself. And now if heart and star happen to fall into the same basin, the distance between them is essentially a characterization of the size of the basin. So heart and star will be a different distance Q0 from one another. But now Clover and the moon, I guess. I guess I did these as Lucky Charms. Did it a while ago. But so they are in a different basin. So the distance between them is not determined by the size of the basin, but the distance between the two basins. And so they now have an overlap Q1 with these, with the strict hierarchy that Q1 is less than Q0. Is this all relatively clear? So what this means is we can consider the formation of the stable glass as one layer, one level of replica symmetry breaking. We have gone from a replica symmetric liquid to this fractured replica symmetry breaking system. The thing that is a big surprise, and I'm not going to tell you the derivation, I'm just going to sort of show you the outputs of this, is that this process actually continues. That once you have formed this stable glass, as you continue to lower the temperature, this stable glass, its basins will break into subbasins. And so this would be two levels of replica symmetry breaking, and you get, again, this sort of fractal-like structure to this overlap matrix, where now you have the distance between two subbasins that are in the same basin, and the distance between one subbasin in one basin and one subbasin in another basin. And one thing we should be clear on, these distances are statistically all identical. Here, it looks like the distance from here to here is shorter than the distance from here to here. But if you imagine this taking place in an extremely high dimensional space, and you don't need to go to high spatial dimension for this to be extremely high dimensional, your configuration space for a system of n particles moving in d dimensions is nd dimensional. So 10 particles in 2 dimensions, and you've already got a 20-dimensional configuration space. More realistic, this is Avogadro number of dimensions in this space. And so the distance between any pair of subbasins is entirely determined by whether they're in the same basin or in a different basin. So they're all equidistant to one another, just depending on the hierarchy. We can continue this, and we could go to 3, 4, 5, etc. But what we find is actually we go from the one replica symmetry breaking through this infinite cascade all the way to what we call the full replica symmetry breaking, or the infinite levels of replica symmetry breaking. And what this is now an energy landscape that is composed of basins within basins within basins ad infinitum. Now, of course, if it's an actual finite system, at some point you do get to the bottom. You can't have an infinite number of, energy basins within a finite system, but the number is enormous. The number of sub, et cetera, basins really grows without bound as a function of the number of particles you have. And then your replica symmetry breaking, your overlap matrix, takes on this hierarchical structure where you have boxes within boxes within boxes, etc. Does this all make sense? Are there questions about this before I continue? So what we call this property is ultrametric. And so this is going to be the subject of the first story that I tell you. I'm going to explain how we can actually directly measure this property of ultrametricity. And then ultrametric energy landscape. Not sure why those came one at a time. So I'm going to show you how we can actually measure this property of the energy landscape being ultrametric. And let me explain to you, when I say ultrametric, what I mean is that we have this property of hierarchy. Another way to think about ultrametricity is we can measure the distance between triplets of replicas. So if we make 3 copies and we let these 3 copies evolve independently as we go through this infinite replica symmetry breaking, each one will get stuck in some subbasin and subbasin, etc. The distance between me and any other copy is entirely determined by what the sort of smallest subbasin is that we are both contained within. So if we have a triplet, 2 of us will be contained generically within a smaller subbasin, and then the 2 of us and the third are all contained within a bigger subbasin. So the distance between the 2 of us will be small, but we will each have the same distance to the more distant third one. And this is the property of ultrametricity. It tells us that an ultrametric is a metric, and a metric is just the set of distances between points in a space. So an ultrametric is a metric that obeys the strong triangle inequality, which is to say that distances between triplets of configurations must form isosceles triangles, and these triangles have to be pointy. So there's a lot of terminology here, metric and ultrametric, but this is the idea that if you take a triplet of systems, 2 of those systems must be very close to one another relative to the third, and they are equally distant from the third. And so this is the feature that we're going to look for in the first piece. And then the second piece, we can think in terms, I thought I had reordered that. So let me do it this way. So the second piece, we can look for a dynamical signature of this replica symmetry breaking. So if we look here, this is the phase space picture that I've been talking about. In the liquid, we can explore absolutely everywhere in the phase space. You can think of it as a big ocean. You can sail to anywhere. The normal glass, the stable glass, we drain that ocean until we're left with a series of disconnected lakes. And if you're within a lake, you can sail anywhere, but you can't sail from one lake to the other. This is our ergodicity breaking. And then the full or infinite replica symmetry breaking is we now form what we call the marginal glass, where each lake has drained into a bunch of subbasins, and each subbasin a bunch of subbasins, and you get this infinite regress, this sort of fractal dust of allowed configurations of our glass. Now, if we think about what this means in terms of the motion of the system, we can think of a thermal particle moving within here. So if we were to track either the entire system or one component of the system, we could measure that system's mean square displacement as a function of time. This is what we do when we're looking for things like diffusion. So in the liquid, we may have a short ballistic behavior, and then at long times, particles will move diffusively. So we'll get linear growth in our mean squared displacement. Once we've fallen into this normal glass, we will get either our ballistic or diffusive behavior, but then we'll hit a plateau. And the plateau is just telling us, oh, I'm stuck. I can't get out. Then we get more interesting behavior when we've fallen into the marginal glass, because as we get these basins within basins within basins, et cetera, the barriers between the sub, et cetera basins get exceedingly small. So what we will do is we will get into one plateau where we see, oh, we're stuck. But then thermal fluctuations will bump us out of one sub-basin into another sub-basin. And we will be stuck bumping from one sub-basin to another sub-basin for a while. And then we will bump out into a bigger sub-basin. And we'll have a new plateau and a new plateau and a new plateau. And if we were to time average, or not time average, if we were to sort of smooth over that, this would correspond to a logarithmic growth. So the signature that we would see is in a liquid, our signature is diffusive behavior. In a normal glass, our signature is we hit a plateau. And in the marginal phase, our signature is we never hit a plateau, we just grow logarithm. And so this then can map out, so this is log scaling in the mean squared displacement. This would then map out our mean field phase diagram for glasses and jamming. I won't talk about this too much for the moment. Maybe jump forward into talking about the actual work. So the first piece is this was done by Cam Dennis, who is a grad student. This is looking directly at the Gardner energy landscape. And our method is to take identical systems, perturb them, and then minimize them to local minima, and use this to directly measure the metric, the set of pairwise distances between minima. So we create a jammed packing, we pick some random direction in phase space, and we perturb that packing, we re-minimize, and then we compute the distance between the minima. And so the obvious way to compute the distance between two minima is just measure the displacements. But there are problems with that because you sometimes have particles that we call rattlers. So particles, you can see right here, that are not constrained by any nearby neighbors. And so they move a lot between two realizations, but their motion isn't what we care about. They're not part of this rigid structure. So what we instead do, and you could argue it's a little overly complicated, we compute the distance between what we call the contact vector matrix. So we make a matrix composed of all of the contact vectors between these particles. And it has the property that the distance between two systems is about equal to the square root of the number of broken contacts between them. And that's the only thing that you really have to keep track of. It's telling me if I've got two systems, if I had to break 10 contacts to go from one configuration to the other configuration, the distance between them is about the square root of 10. Our algorithm then is that we want to construct this metric for a whole bunch of nearby energy wells. So we begin with some minimized configuration, some zero temperature jammed configuration. Pick a random direction in our high dimensional configuration space. Pick a uniformly distributed random length along this direction. The fact that it's uniformly distributed doesn't really matter. We just want a way to sample a whole bunch of nearby minima. If we're sampling very far away minima, then all of the minima will be far away and we won't learn anything about the hierarchical structure. So we want something that gives us a bunch of really close together nearby minima. This seems to do the trick. We move along that vector and we reminimize, and then we compute all of the pairwise distances to every other well. Then we sort this with a clustering algorithm. So what we've done here, this is at a particular pressure, so this is very close to the jamming transition. We've made about 410 here, different distinct minima, and we've computed all of their pairwise distances and we've sorted them. And we see what looks a little bit like this ultrametric structure. We see boxes within boxes within boxes. Out here, you see these are wells that are very, very far from one another. They're sufficiently far that we don't see any structure in them because we're only sampling about 400 nearby minima in a system that, I think this is a system of 256 or 512 particles, and it has, would roughly estimate about that number factorial minima. So this whole configuration space contains an astronomical number of minima, and we are trying to find a bunch of local minima and looking at their structure. So then we can first look at the dynamics as we minimize. So as we take our systems and minimize them, we can compute the distances as a function of the number of iterations of a minimization algorithm. So this plays a little bit the role of temperature. This is sort of saying how deep within our minima are we exploring. So we start out and everybody is replica symmetric. And then as we minimize, we begin to see, oh, all of these are falling into the same well. And then we see, oh, within that same well, different ones are falling into different subwells. And then within those subwells, they're finally refining and getting all the way to the bottom. Yes.
Yeah, is there anything interesting to be gotten from like the, I don't know, measuring the fractal dimension of that graph on the right, or is it just kind of?
Maybe I wouldn't want to pull too much quantitative out of this because these dynamics are dependent on the choice of our minimization. It's more that there is this general feature, whatever minimization scheme we use, you get this hierarchical choosing of first the basin, then the sub-basin, then the sub-sub-basin, etc.
How are you writing the dynamics? You just like pick these spheres and then.
So what we do is we grab these spheres, we say that there is a contact potential between them. We usually just use, Hooke's law overlap. So a harmonic contact potential. That means if they're not touching, everything's cool. If they're overlapping, they get pushed apart with a force proportional to the overlap. And then we use it's called a fast inertial relaxation engine, FIRE. We also could do this with just steepest descent or gradient descent or any of these Newtonian methods. It really doesn't matter. We just do some form of energy minimization to minimize all of those overlaps and find a local minima. Does that answer your question?
You're not doing Newtonian dynamics. You're trying to minimize the energy of the system.
Yeah, although you can think of Newtonian dynamics plus damping are effectively a minimizer. If we were doing just Newtonian dynamics, we wouldn't ever lose energy and we would always be at a fixed temperature. But instead, we're trying to find what people call the inherent state, the local minima associated, and that allows us to measure the distances between the minima associated with each of these subbasins. Yeah.
So I know that fire isn't perfect and it adds noise, and we know that fire isn't the best if you want to find the inherent minima.
Yes.
So would that mean that there's a limit to how minimized you could be in here?
So there's a distinction. So the issue is that all of these different minimization schemes, they don't do a great job of producing the true inherent state based on where you started. But our game is not to find the true inherent state. Our game is to find a whole bunch of nearby minima. And so any scheme is sufficient to find a whole bunch of nearby minima. I'm not claiming that this is every single minima within some distance of my starting point. All I'm claiming is that this is a bunch of them. And if we sample them in whatever way we like, we always find this hierarchical structure. If you don't believe this, which you should, it looks compelling. We can actually make the degree of ultrametricity quantitatively accurate. So what we can do, and I won't talk about this now, but if you're interested, ask me because it's kind of fun. We have above the metric and then a little zoom in on the metric so you can see it's really got this nice hierarchical structure. And we do this at two pressures. The scale of the pressure doesn't really matter. All that matters is this is relatively far from jamming. This is much closer to jamming. We can compute a thing called the subdominant ultrametric. This is what the metric would be like if it perfectly obeyed this ultrametric structure. If it perfectly always had these isosceles triangles. You can see this means that these sort of rounded edges become nice sharp square edges. And then the fact that it's the subdominant means it is the metric with distances that are as close to without going over the true distances. So what we're doing is we're saying if our system were perfectly ultrametric, then the subdominant ultrametric and the true metric would be identical to one another. So you can see here the subdominant ultrametric, and we've drawn some lines on it to sort of show you the hierarchy. And you can compare visually how similar are the two. I would argue they're quite similar. We can do something that I think begins to seem like parity. We can define a metric on the distance between the true metric and the subdominant ultrametric to ask ourselves how far away they are. And so this is what we do. We characterize the distance to ultrametricity. And this distance is 2.7. And what this distance means, we don't need to go into that, is that you would always need to break about 5 bonds to get from the actual metric to the ultrametric. In other words, if you took the system that is at the minima, it's always about 5 broken bonds away from where it would have to be if it were perfect. And now you can say, if I've got a small system and it's 10 particles, breaking 5 bonds is a big deal. But what we find is that this number is independent of the number of particles. So here, this is a plot of this distance to true ultrametricity as a function of sort of a scaled number squared times pressure. This is the important scale in the system. And we do this for systems of 64 up to 4,000 particles. They all collapse onto the same curve. And as we go towards this low pressure, as we get closer and closer to the sort of truly jammed state, they are always only about 5 broken bonds away. So 5 broken bonds in a system of 4,000 particles is not much. And then if we consider in the thermodynamic limit where n becomes extremely large, this is really a statement that this becomes exactly thermodynamic in the exactly ultrametric in the thermodynamic limit. There's nothing else going on. As we get bigger and bigger, the system gets more and more perfect. So, let's see. Okay. So that's the story of ultrametricity. And I think it demonstrates to us that jammed systems, this sort of zero temperature version of jamming, really does have this ultrametric replica symmetry breaking structure. We can do something even better in the eyes of physicists, which is we can do direct experimental measurements. So Gardner in practice, and this is done by Andy, So our model system now is a colloidal suspension, which is a glass former. It forms what we call a colloidal glass. So we take this suspension, we let it sediment, and everybody kind of gets in everybody's business, and it forms a solid. So these are PMMA colloids. They have a diameter of 50 microns. So they're very large compared to what you usually think of when you think about a colloid. I'll explain why in a moment. Within this, we index match them. And so you're not seeing all of the colloids. You're seeing about 1 in a few hundred of the colloids, which we have dyed black so that they can act as tracers. We subject them to slow and gentle sedimentation. Basically, we shake them up and then we leave it alone. So you can see here the change in density as a function of time. We shake it up, and then after 100 minutes, it's increased by about 4%, its density. And then it continues to densify for the entire time we're able to measure. And this entire time we're able to measure is basically overnight. It's the time between when most everybody leaves the physics department and when the cleaning crew shows up in the morning, and their vibrations ruin our measurements. So I'm going to show you, and I'm going to click on it. So click on it here so you really believe me. This is high-speed video. This is a video taken at 60,000 frames per second of a single colloid, so a single 50 micron colloid. We illuminate it with a really bright light, a half-watt LED, and we use a radial center algorithm to localize these particles. And we're able to localize them down to about 2 nanometers, but then their noise is IID, so we can even do better. So I'm sure, I mean, everybody loves looking at high-speed video, so I'm sure you're just absolutely entranced by this. What we can see is we can then take this whole video and we track it, and we can see the motion of the particle. And from this, we can make amazing measurements. The reason is as we continue to zoom in, we can actually track this 50 micron particle on length scales of nanometers really, really, really accurately. And this is the reason why we use such a big particle. If you use a big particle, the information is spread out over a large region of your image, which means that you can localize it very well to a sub-pixel resolution. And then the thing that is obvious but hard to reason to yourself is we all think about small particles as subject to much more thermal fluctuations. And they are on the scale of themselves. However, large particles move farther thermally. A bowling ball at room temperature is jiggling around much, much more than an atom. It's just that the atom is moving a lot more relative to its scale. And so this 50 micron particle, the bigger particle that we use, the more that it's moving. So our goal was to essentially get the biggest particle that we could use that would fit within the confines of our zoomed in high-speed camera and would have the right optical properties and sedimentation properties, etc. So the point is that we can measure this one particle extremely well. We can use this.
Wait, did you play the video?
Yeah, it was playing the whole time.
I don't believe you.
So let's see. See? Okay, no, you don't believe me.
Okay. Okay, now I see it.
It's just going nuts.
Yeah, okay.
I mean, it's just crazy.
You're pulling our legs with this one.
That's
the movement, okay.
Sorry, with a radial center algorithm, is the amount of information you have about the particle center proportional to the number of radial pixels you have ish?
Oh, I don't know that I can answer that question. What I can tell you is that this algorithm for finding center points is computationally very fast And it gets very close to what's called the Kramer-Rao upper or lower bound, depending how you're talking about it. It extracts the center as well as you possibly can, given the noise within your imaging system. And for us, that is an IID localization noise of about 2 nanometers. And then what we can do is we can look at the motion of this single colloid when the system is in the liquid state. So I shake it up, I put it down, I wait, a few minutes, and I can look at it for times between about 10 to the minus 5 up to close to a second. And I can measure its mean squared displacement. And amazingly, I can actually measure the crossover from ballistic to diffusive motion. So in blue, this is ballistic motion. So this has a slope of 2 or a power law of 2. Here is diffusive motion. You'll notice this mean squared displacement goes down to 10 to the minus 19 meters squared. This corresponds to a couple of angstroms. But I had told you that the IID, that the localization noise was 2 nanometers. But because the localization noise is random, it gives you a noise floor that you can subtract away. And you can get another decade or so down in mean squared displacement. So this tells me that we can measure the liquid state very, very well. And indeed, this colloid is initially part of a liquid of colloids. The liquid to stable glass transition, we would expect to see as we increase the packing fraction, we go from diffusive behavior to getting a little bit caged and more caged, and then eventually completely caged, stuck in a plateau. And then we would expect, as we get into the marginal glass phase, this plateau falls and becomes a logarithmic growth towards the plateau. So as we go through this sedimentation, we shake it up and we see ballistic to diffusive to a little bit subdiffusive. So I apologize, I lied to you a little bit. This is measurements done in very, very low density colloids. So this is a single colloid just jiggling around in water. This is measurements done in our sedimenting colloid. And I think you would agree that this looks somewhere between diffusive and subdiffusive. It's what you'd expect to see in a dense liquid. And then here, I'm also showing the mean squared displacement versus time on a log linear scale, so that if there is logarithmic behavior, it would show up as a straight line. So as we continue to wait, it in fact does bend over towards something that looks like it's stuck in a plateau. And then this becomes straighter and straighter, looking more and more logarithmic. And so these last two, I've just drawn straight lines. So these would be logarithmic growth lines. So the claim would be that this constitutes direct evidence for this Gardner phase, that we have gone into a stable glass here where we hit a plateau. And then as we continue to sediment, this stable glass falls into the marginal phase. And here we can compare this to a predicted phase diagram of sort of soft colloidal glasses, where at a fixed temperature, as we increase the density, we should be liquid and then a stable glass, and then through this marginal glass, and actually back into the stable glass. And what we see as a function of time, evidence here, I'm just showing the log linear scale, that we are non-logarithmic, non-logarithmic, logarithmic, and then non-logarithmic again. So this, I would argue, is direct experimental evidence of this Gardner phase. And with that, I will leave you that this Gardner phase is not only theoretically appealing, because it finally gives you a handle on how to understand the glass transition, but it is something with direct experimental evidence and something that we can interrogate by directly probing the energy landscape. So thank you for your time and attention. I'm happy to answer any questions.
Thanks.
Yeah, what the heck is going on with that up? Sorry, can you scroll back a slide?
Yeah.
What's going on with that? Why is there a marginal inclusion in the stable glass phase? Is there a
So this is short answers. It's complicated, right? This is you get this sort of reentrant behavior as you continue to densify with these soft spheres. It's predicted that you get this called a Gardner dome, and then eventually you get into the sort of long time marginal glass phase. The details are very complicated, basically. I haven't been able to think of an intuitive way of explaining why this happens. It also is frustrating because a very obvious question is, well, why didn't you just wait longer and then go into this, the sort of low dent or the high density marginal glass phase? And it's because these measurements are very, very vibration sensitive, right? Because we're looking at the thermal breaking of these marginal structures. So they're by definition very, very weak. And so in the morning at about 6 a.m., when people come in to clean, all of that's the end of the measurements. We can't do anything more. This data set that we put into the paper was actually gathered on, I think it was Memorial Day weekend when almost nobody was on campus. And so without really extraordinary vibration isolation, we're limited to something on the order of the 8 hours of overnight data gathering.
Questions? This is like slide 5 or 6.
Yeah.
I'm kind of curious how you go way back. Okay, next. I'll let you know when. No, this one. Go back. One more, that one, yeah. Okay, so you said, I didn't really understand it. You're saying that this Q1 quantifies like the overlap between the clover and the heart?
Yep.
Or the clover? Yeah, you say the overlap between the clover and the heart is the same as between the clover and the star?
Yep.
And how are you quantifying, how are you measuring overlap again?
So here, this is the theorist world.
Yeah.
They say overlap and they don't care.
Yeah, I don't really carry the vote.
What
How do you actually, yeah.
What we actually measure was we measure the distance. And so distance is different from overlap. Overlap is bounded between 1 and 0. Distance is bounded between 0 and the system size. So what we measured was you take the system, you enumerate every set of contacts, and then the vector that you draw between every particle and its neighbors, and you turn that into a contact vector matrix. It's a D by ND matrix. And then you ask, what is the distance between the matrix associated with one minima and the matrix associated with another? So what we would say here is that these two, which fall within the same minima, the distance between them is small. Maybe you have to break, 3 bonds between them. But between this pair and this pair, between any pair of them, maybe you'd have to break 50 bonds, right? So in practice for systems of finite size, it's not the case that all of these Q1s, that all of these values are identical. It's only in the limit, strictly speaking, of n going to infinity and spatial dimension d going to infinity, that this all become precisely Q1. However, in a physical system, all of the values in this region of the matrix would be very close to Q1 and easily distinguishable from these other values.
Questions?
So you're taking this replica symmetry breaking and you're using packings as a way to model it, or as an analogy. With evidence from an experimental setup that packing and reproduce or is evidence for replica symmetry breaking.
Yes, what we're saying is that the ultrametricity is evidence that jammed packings exhibit replica symmetry breaking.
Gotcha. Yeah. Do people explore other types of analogies or other types of mathematical objects, for example, to take this replica symmetry breaking and
Yeah, so one thing that people have talked about is whether the structure of folded proteins also goes through replica symmetry breaking. How it is that you can have, as you fold, you get for certain proteins, they all fold into generally kind of the same shape, but then they have a series of decisions that they have to make. And as they go through that decision making, going down to a final ground state, the thought is that this might also be the result of a full replica symmetry breaking process. In terms of more abstract mathematical objects, less sure about that. I know that we model lots and lots and lots of things as being glassy, and those things would also have this structure. So things related to, ecological dynamics, things related to where it shows up a lot is this is a little, I'm over my skis, this cat's rice stuff within math that might be familiar. Or this, you can also see this in the structure of random functions. So just the set of minima that come from random functions. So this kind of stuff does show up in other mathematical fields. And it's an issue because the mathematicians, they believe the outcomes of this, replica trick stuff, but it's not provable. And so they don't like it.
is it proven that it's not provable? Is it just it hasn't been proven?
It hasn't been proven. People would like to. What usually happens is you use this replica symmetry breaking to get the answer, and then you use something like renormalization group or other techniques to prove that particular answer. So replica trick it's a good tool, but it's just the fact that it gives the answer doesn't mean that the answer is right.
So Eric, I have a question.
Yeah.
Which part of your work and approach is gonna be translatable into what Axel is trying to do
So I think that
on these spin chains?
the most obvious is the high performance computing. So I didn't lean into this so much in the description, but so this work, so this is 500 systems. This is 5,000 systems. And this took up, this is really massive scaled GPU computation. And so this idea of how do we work with these extremely large systems in which we're doing essentially minimization is essentially the same problem in a very broad sense of taking these 1D spin chains, which exist in a dimensionality of something like L choose N. If L and N are both big, the dimensionality of this space is enormous. These are also working within these enormous spaces. And so how do we extract meaningful results from that? So I think that's what we're hoping will be useful.
Yeah, I had Nick and I had written code of like what we're trying to do. It was a proof of concept more than anything. And Eric's really taking it and optimizing it and parallelizing it and actually like taking it to its limit. And question.
Yeah, I don't know if this question is fully formed, but you showed how as you do more iterations or you're sampling more of those minima that the picture sort of evolves or becomes more clear.
Yeah.
Then you talked about measuring sort of the distance between the result of that sampling versus true ultrametricity,
Yep.
does that distance get smaller as you sample more minima?
So as you sample more minima, the distance doesn't really change. And you have to be careful because if you sample minima that are all outside, are all very far from one another, you don't see the hierarchy, but everybody is equally distant. And if everybody is equally distant, then all of your triangles are sort of by default isosceles because they're all equilateral. And equilateral triangles are isosceles. And so that's why it's important. You see that we've got this sort of green rim. These are the systems that you can think of as sort of in the ocean. They're as far away from one another as they can be. And we could cheat it by having more and more and more of that, which is by default ultrametric. And so we make sure that we stay close enough that we don't have much of that and that we're actually measuring the distance from ultrametricity of, the core of this. As you zoom in, this is why we went to the 5,000 system matrix or metric. As you zoom in, this distance from ultrametricity doesn't change until you get real close.
Other questions? I had a question related to Nick's.
Yeah.
How do you know when you have a replica symmetric braking system?
So
Or do you have to go through this, or is there like some like heuristics ahead of time that would lead you to believe?
no, I mean, so from a theory point of view, you can, here I can try to. So from a theory point of view, you can make, and I'm not gonna show you much about this. So you can talk about like the spherical p-spin model, and in that one, you can see where here it is, right? You can add in the replicas and you can see with some real work that you get to a point where the replica symmetric solution breaks. It gives you essentially a negative entropy. So when that replica symmetric solution gives you a negative entropy, it's telling you that there's no longer a replica symmetric solution. You have to have replica symmetry breaking. So this is one way you can attack it theoretically and show that replica symmetry breaking has to happen.
Mhm.
Alternatively, you can attack it empirically by looking at these signatures, looking directly for the ultrametricity. And it really just depends on what the problem is and what the tools you have access to are.
Those sound like a lot of work.
Yeah, I mean, it's not easy. The other way, so the heuristic is if the system gets stuck in a frustrated state, it's probably breaking replica symmetry. And so, and this showed up in the previous talk where we were hearing about the system falling into local minima. So if these local minima become so dense that you can never hope to find the global minima, then that very well may be a case of replica symmetry breaking. And you can think of it in terms of a glassy system. So, thinking about glassy spin chains is very interesting. It connects a lot to these, spin glass ideas. So that would also be interesting to think about. Yeah. Soothing.
Well, let's thank Eric one more time. Before we all leave, I want to thank everyone again one more time and announce that we are trying to make this a recurring event. So in the following days, I'm gonna follow up and send you guys an email to try to get feedback of how we can continue moving forward and try to have this event like once a month for a while. And but yeah, let's thank all the speakers one more time.
Thank you so much, Axel, for organizing. Thank you all for coming.
Yeah. Yeah, no problem. So
Is there like a way to bootstrap it?
Actually doing
If you have some
Yeah, I like that. Yeah, that was good. Gave us like a
random